This is lesson 6.3, separable differential equations. Separable differential equations. Now first of all, we're going to talk about what is a differential equation. So let's look at our first example. This is a differential equation, and the way I know it's a differential equation is that it's got dy dx on the left side, which tells me that this is a derivative. If it is a derivative, then it's called a differential, and so this is a differential equation. Now, it's a separable differential equation because we are going to be able to put the x's on one side with dx and the y's on the other side with dy. Not every equation like this is separable, but the ones that we're going to learn about, the ones we're going to deal with in A, B, and BC calculus, will be separable. So to begin with, I'm going to take this equation, and I'm cross multiplying. And the reason I'm doing that is because you see the dy here, and you see that y is over here. So I want to try to get them together. And the same thing with my x's. I have x's on this side in the top, and dx is on the bottom. So the quickest way to get the x's with dx and the y's with dy in this case is to cross multiply. Now once they're separated, as long as my x's are with dx and my y's are with dy, then I can integrate both sides. So on the left side we're integrating x squared plus 2, and that's going to become x to the third over 3 plus 2x plus c. On the right side I've got 3y squared, which would become 3y to the third over 3. Now usually this would also have a plus c, but let's say if I did do plus c on both sides, what happens when you subtract c? You can see that the c's would totally go away. So instead of putting plus c on the right side, we only put the plus c on the x side. Okay? Whichever side has x is where we're going to put the plus c, and that way it won't get canceled out as we work through the problem. Now this problem is mostly done. We just want to try to get the y by itself. So I am going to divide the 3's out. So that's going to give me 1/3 x to the third plus 2x plus c equals y to the third. To get rid of the third power, I'm going to do the cube root on both sides. Now this is a big old cube root on the left side. So my solution now is simply y equals the cube root of 1/3 x cubed plus 2x plus c. Just like that. We want to solve these for y. You're going to see in the examples that we'll do from the AP test that they always say to find it in terms of y, or they'll say they have notation that indicates to you that y needs to be by itself. Alright, so let's try the next one. This one is xy prime equals y. So the first thing I always do, if I have a y prime, recall that y prime is just another type of notation, and it's the same thing as dy dx. And I go ahead and change that because we need the dy and dx to be separable. So first of all, if you look at what our problem looks like, I need to get the dy on the same side as y and the dx on the same side as x, but the dx cannot stay in the denominator. So I'm actually going to go ahead and multiply the dx to the other side first. And then what I'm going to do is on the right side and left side divide by y, which leaves dx by itself. But at the same time I'm also going to divide both sides by x so that the x's cancel. So now you can see that what I've got is dy over y equals dx over x. So not only do I have to be able to separate the variables, in the process of separating it I also have to make sure that the dy and the dx are always either in the numerator or that it's just a whole number with no fraction. Dy and dx can never be in the denominator. Now that they're separated, I'm going to integrate both sides. dy over y, if you remember, is in the format of du over u, which means it's ln, absolute value y. And on the right side, I've got ln, absolute value of x, plus c. Now I've talked about this before, that you use the absolute value bars until you know that you don't need them. And in this case, we don't know. We don't know that y and x will always be positive numbers. So I'm going to keep the ln's for the most part. Now here's where this gets a little bit tricky. I want to get y by itself. So how do I get y by itself? Well, to get rid of ln, the only thing that I can do is put e to that side power and e to this side power. Okay? I'm probably going to need to erase some space here, but what happens with e and ln? Well, e and ln are inverses. They cancel each other out. That leaves me with y here. Now, I know that it's going to have to be a positive y here because e to any power is going to be positive. So I have y equals e to the ln x plus c. Okay, and this is the first time you'll see it, but you'll see it many times. When you have exponents that are added, you can separate them into exponents with the same base that are multiplied. See, e to the ln x times e to the c. If you think about this going backwards the other direction, what do you do if you have the same base? What do you do with the exponents? You add them. So what we're doing is we're taking exponents that are added and we're taking them backwards in the process, and we're changing this to e to the ln x times e to the c. Okay, and here's what gets most people. E is a constant, c is a constant, so e to the c is still a constant. And e to the ln x, e and the ln x are inverses, and so we're left with x. So when I integrated x, y prime equals x, I got y equals cx, which is linear, which may surprise you. Okay, you're going to see a little bit more of this, so let's try some more examples. Alright, so first of all, on this problem, I'm going to change my y prime to dy dx. Probably hear my daughter screaming in the background. That's always fun. The first thing I'm going to do is add the 3e to the x to the other side. So 4y dy dx equals 3e to the x. Now, remember what I said about dx not needing to be in the denominator. So I am going to multiply that to the other side. So now I have 4y dy equals 3e to the x dx. Now my variables are separated. It doesn't really matter where the 4 ends up, and it doesn't really matter where the 3 ends up because they are coefficients and they're constants. But it's very important that my x and my dx are separated from my y and my dy. Once that's done, now I can integrate both sides. 4y dy becomes 4y squared over 2. 3e to the x becomes 3. The integral of e to the x is itself, and then we have plus c. So, simplifying this, I have 2y squared equals 3e to the x plus c. Divide both sides by 2. So I have, following my little tracks here, y squared equals 3 halves e to the x plus c. Now you're probably thinking, if I divided c by 2, isn't it c over 2? Well, if I take a constant and I divide it by a constant, don't I just get another constant? Some people even write this as c1 or c2 just to remind themselves, but it's really just another constant. Now I want to get rid of this square by square rooting both sides. So, following upwards, y equals the square root of 3 halves e to the x plus c. And that's my solution. Okay, the solutions that we have been finding so far have had c's in them. Go back and point that out. There's a c here. And if there's c in there, then it's called a general solution. It's general because c, we don't know what it is. The next type of problem we're going to look at is if you have a particular solution. The process is going to be pretty much the same, but at the end I'm going to use this information on the side to find out what my C is. Once we know what C is, then we're looking at a very specific solution, not one that's general. So to solve this problem, I'm going to start off by changing my y prime to dy dx. And I'm actually going to go ahead and at the same time move ln x squared to the other side. I'm adding it over here to 0, so I just have ln x squared. Now I need this dx to go to the other side, so I have 2x dy equals ln x squared dx. And then I need to get rid of the x. I can take the 2 with it, but I think I'm just going to take the x here. So I have dy equals ln x squared over x dx. Okay, so this looks like a real challenge for us, because if it's time to integrate this, some parts are really easy and some parts are really not easy. How do you integrate dy? Well, where did dy come from? It's just y. But what about this ln x squared over x part? Can we do a quotient rule in integration? And the answer is no. Can we integrate ln x as it is? The answer is pretty much no. So we're going to do a couple things. The first one I want to do is bring that 2 to the front, so that it's y equals integration of 2 ln x over x dx. And now I'm going to go to the next page and we're going to do some u's. Okay, so y is currently 2 ln x over x dx. This part's an integral. I don't know if I had that. Yeah, I did. Okay. So I have to do some u substitution here. So with my u substitution, I'm going to say u has got to be ln x because I don't know any other way to integrate it. And so what would my du be? The derivative of ln x is 1 over x dx. So with a little bit of rewriting, let's pull the 2 out. I'm going to write this as 1 over x times ln x dx. So you see my u is right here. And you see that the rest of this is the du. So this is 2 integral u du. If I just plug in what I've got. Okay? So now I can integrate it. Y equals 2 times u squared over 2 plus c. So my y equals u squared plus c. So my y equals ln x squared plus c, because my u is ln x. Now I did have some initial conditions, so let me look back and see what that was. Y of 1 equals 2. Now keep in mind this always takes the format of like a coordinate. So that's the x value and that's the y value. So when x is 1, y is going to be 2. When x is 1, y is going to be 2. So plug 2 in for y. Plug 1 in for x. Hopefully some of you see where this is going, because what is the natural log of 1? It's 0. Doesn't matter if we square it or not, it's still going to be 0. So c is going to equal 2. So what is my full, complete, particular solution? Y equals ln x parentheses squared plus 2. Okay? Leave yourself a lot of room as you're working these problems. So let's look at another one. And I'll kind of tell you what I call my steps as we go through this. The first thing I say to do is to separate. So we're going to separate our variables. So I'm going to have y dy equals x dx. Okay? So we have separated. That's the first thing. So separate, integrate. So y squared over 2 equals x squared over 2 plus c. My plus c always goes on my x side. So we've separated, then we integrated, And now what I call the next step is pluggerate. We're going to plug in the values here. So separate, integrate, pluggerate. So when y is, this is x and this is y, remember. When y is 1, x is going to be 0. And you know 1 squared is 1 and 0 squared is 0. So what I have here is 1/2 equals c. So my c is simply 1/2. So what's my solution then? Well, let's see. I had y squared over 2 equals x squared over 2 plus my c, which is 1/2. I like to do all of that plugging in early before I start trying to simplify stuff, because remember now, y has to be by itself. So I'm going to multiply this whole problem by 2, which makes me have y squared equals x squared plus 1. And then I want to get rid of my square, so square root both sides. And y is going to be the square root of x squared plus 1. Now, you know that when you take the square root of something, it's usually plus or minus. So how would we know if this one was going to be plus or minus? Well, what we would do is we'd go back and look at what happens at 0, 1. Is this equation at 0, 1, is this going to be where the slope is going up, or is this going to be where the slope is going down? So when we plug 0 and 1, if we plug that into the original equation, that would give us, what, 0? So, I don't know how helpful that is, but if I plug it into the equation that we're looking at, then it's actually going to be the positive part and not the negative part. So let's see if I can get that out of there. There we go. Okay. Now the best way to do this, to know if it's going to be positive or negative, is to actually look at what the graph would look like. We're not going to do that right now, but when in doubt, you can always leave your plus or minus until you know for sure which direction it's going to go.